right to the end, okay? So that's chapter 8 in a nutshell. What chapter 9 does is really just, I'm not sure why it's divided the way it is, but it starts talking again about these alkoxide ions here, like the ethoxide ion or the methoxide ion. It just goes into a little more detail about how you make them. But don't get wrapped up in that. The study guide, which I have it right here, I haven't posted it yet.
Chapter 11.
As soon as I get back to my office, I'll finish it up and post it. Just work with that and know what is doable. And in terms of organic chemistry, going forward, you're not going to remember very many specific reactions. In fact, even though I do this for a living, organic chemistry and organic synthesis, I don't remember a lot of specific reactions, but I have a sense of what's doable and what's not doable, what types of reactions are likely to occur or not likely to occur. The details of exactly how to make a reaction work, I can always look up. So, if you need to do something, you need to know that it can be done. You can look up exactly how to do it later on. That's oversimplifying a bit, but you don't have to have an encyclopedic knowledge of chemistry. Some of the most proficient synthetic organic chemists that have ever lived have actually had bad memories, never remember any specific reaction or how to run any, but they can look at a synthesis problem and say, well, you could do this, you could do that. It's sort of like the difference between a carpenter who actually has to build a room on your house and the architect who says, I envision this structure here and I think you can do this and you can do that and this is how this is what I want done. You figure out how to get it done later, but this is what I want done. So being an architect is much more powerful than being a carpenter. Not that there's anything wrong with that, because in the end, somebody has to make it happen. And in organic synthesis, if you go to a big pharmaceutical company, for instance, most of the lazy PhD chemists just sit there and act like architects and say, I think I'd like you to try this, and it gets passed along to the underlings to actually make the reaction work. Make it so, if you will. Just go away and come back when you have this reaction completed. But they themselves probably don't know exactly how to do it, but they have a sense that it could be done. So don't worry about the details there, but just look at that beginning of chapter 9 on the alkoxide ion. And then it talks about this protonated OH business, so you've already had that. The new thing that's there in chapter 9 is a closer look at carbocations. Because when you protonate alcohols, they have a strong tendency to form carbocations. Because the protonated OH as a water molecule is such a good leaving group, even though carbocations are bad news, it's almost like it can't resist. It just wants to form that stable water molecule so badly that it puts up with the carbocation. So in acid, alcohols form carbocations. And what kind of acid do you want to use? Well, you can't use protons themselves. You can't have a bottle of protons. You must use an acid. Same way you can't have a bottle of sodium ions or a bottle of hydroxide ions. You can add sodium hydroxide or potassium hydroxide, but you can't add hydroxide. So you can add HCl, which will generate protons, or you can add sulfuric acid, which will generate protons. but you can't just add protons. The problem is that because you have to deliver the proton with a conjugate base, so if you use HCl, for instance, that does generate protons, but also generates a conjugate base. And if all you want is action from a proton, you have to hope that that conjugate base is dormant, and it doesn't do anything, it just sits there. That's not necessarily true. A chloride ion, for instance, is quite reactive. It's a very good nucleophile in particular. So if I use HCl here, and I produce the carbocation plus water, that chloride ion is not going to remain dormant while these carbocations are floating around. It's going to react with the carbocation. So once the carbocation forms, R plus and Cl minus are eventually going to find one another and react and produce RCl. Now this is fine if I want to make RCl. If I don't, then what's the alternative? The alternative would be to use an acid that has a high probability of producing a conjugate base that is dormant. There are two that are commonly used. Sulfuric acid is a good one because the conjugate base, the bisulfate ion, is a very big, lazy anion, very stable. Doesn't really want to do anything. So it tends not to get too involved. It can, but much less so than a chloride ion. So if I wanted to produce a carbocation and maximize its lifetime, sulfuric would be a better acid than HCl. The other one that you see a lot is phosphoric. Which does the same thing. Phosphoric acid, particularly those of you who are biology or biochem majors, are familiar with that, forms dihydrogen phosphate, actually has 3 ionizable hydrogens, but the first proton that's most acidic produces the dihydrogen phosphate. Use this a lot to produce buffers. And that also is a very stable, unreactive conjugate base. So the closest thing to just adding protons is a little bit of sulfuric or a little bit of phosphoric. And you see that a lot. And again, the stability is not just due to the huge size, it's due to the fact that the negative charge is stabilized by so many oxygens. And it's difficult to write all of the forms where the oxygen is positioned on all of where the negative charge is positioned on all of those oxygens, but it's shared by the 4 oxygens in the bisulfate ion and the 4 oxygens in the dihydrogen phosphate ion. The chloride ion is stuck with it all by itself and is more reactive. Now where this comes in, I'll finish with this, is an important reaction called the dehydration of alcohol.
Yeah, alcohol dehydrates you.
Dehydration, for instance, of cyclohexanol which we used to do in the organic lab, is where you remove the elements of water from two adjacent carbons, the OH and a CH next to it. And in place of the water, you get a carbon-carbon double bond. So the dehydration of cyclohexanol produces cyclohexene. And this is traditionally done with sulfuric acid. So picture this. Stepping it through a mechanism, if you take an alcohol and put it in the presence of a strong acid, there's only one thing to do: protonate the oxygen. This is simple acid-base chemistry. You've got a strong acid, strong proton acid, the oxygen is the Lewis base. Put two and two together, protonate the OH. Now don't worry about what happens after that. When you're writing or trying to figure out how a reaction works, take baby steps. Just go one step at a time. You may walk off in the wrong direction, but you'll find that out eventually, come back and take another whack at it. Just don't try to swallow the whole thing at once. Just try to say, what is a reasonable thing that might happen, and where do I go from there? So when you protonate the OH, if you recognize that that's a good
What did you
leaving
write
group
before when I was gone? Before this?
and tends to form carbocations, then I'm going to remove that protonated OH as water and say, okay, now I have this carbocation.
Carbocation.
The way that the carbocation gets to be the alkene is by the most favorite thing that carbocations do to stabilize themselves. Now you always want to see a carbocation as a very desperate carrier. It's very high in energy. It'll do whatever it has to do to get rid of that plus charge. To get rid of a plus charge, you've got to form another bond to that carbon. That carbocation has 3 bonds, supposed to have 4. So what carbocations do is they look around for bonds that can be stolen.
Transition state complex.
So this is a carbocation, and it's looking for electrons. There are pairs of electrons staring it right in the face. So remember, your carbocation is planar. On an adjacent carbon, if you have a CH, for instance, that carbocation is looking right at that pair of electrons like a dog looking at a steak on a table. It's going to steal it. Can't help itself. So it grabs that pair of electrons and turns it into a pi bond and sets the proton free. So the proton is lost out into solution. Goes out to a water molecule, for instance, and leaves you the carbon-carbon double bond. So it's a loss of water from 2 adjacent carbons triggered by the protonation of the OH, which forms the carbocation that eats a pair of electrons from a neighboring CH bond. Now actually, it will even do that if that's a carbon-carbon bond next to it. Even if this is a CH3, it can do that. But mostly it does it with hydrogens. So when a carbocation forms, right next to it, it's going to spit out a proton and invest that pair of electrons that's left behind into a pi bond. Then it becomes a very stable alkene, and your proton is just out there in the water. So that's not a problem anymore either. So the energy goes way up and then goes way back down again. It's actually a pretty good reaction. So any alcohol can do this as long as it has a hydrogen next to the OH that it can lose. It has to be able to lose water. But this is a very, very good reaction, and it's actually reversible, because if you protonate the carbon-carbon double bond, just go backwards, you get the carbocation, and then if you have water present, that can react with the carbocation to give you the alcohol. So this goes back and forth. To make it go this way, you minimize the amount of water and actually probably try to remove it as it's formed. That's not hard to do. If you wanted to go this way, you would add a ton of water and push it all back towards the alcohol. So alcohols can be converted to alkenes by dehydration, and alkenes can be converted to alcohols by hydration, the opposite reaction. Okay, let's stop here.
Music to my ears when he says let's stop there.